Welcome everyone to QSI online seminar. Today our speaker is Ferrie, and he's an associate professor at UTS QSI. He has significant experience in learning algorithms and software they could be using in optimizing quantum circuits with various applications, including tomography. And he has a growing research group at QSI, and I'm one of the postdocs of the group. Today, he will talk about self-guided quantum learning. So please start.
Sorry, Clara, let me see if I can get my screen up here. Can that be seen?
Yes.
Okay. All right, well, it's going to be fun to give this talk. Interesting to do it virtually. So as Clara mentioned, I have a research group at UTS, and they're all doing wonderful work, but I have yet to get comfortable talking about somebody else's work. So they're all doing great work, but I'm going to talk about some of the work that I've done myself. So that's going to be a little bit older, except there's been some recent updates, and I will also go over some open questions near the end. So the title is Self-Guided Quantum Learning, and ostensibly it's about tomography. So I'll overview the problem of tomography, and then I'll talk about the particular protocol, the self-guided tomography protocol, and then some applications at the end. Okay, so just to remind everyone, what is tomography? In quantum physics, a modern sort of operational interpretation of it, we have three things that can happen to a quantum system. First, you prepare some physical system, then you make some changes to it, and then you perform a measurement and read some output on some meter somewhere. Now, this is, in some sense, textbook quantum physics. If I'm told all of these things, then an assignment question or an exam question would be to calculate this probability here. So this is called the Born rule. And the calculation that you have to do is something that requires linear algebra and possibly differential equations if you have to solve a Schrodinger equation. And what's not often talked about in introductory quantum mechanics courses is kind of the opposite question. So now in a lab, I may know what I'm able to do to change physical systems. I have a very good sense of what I'm doing when I perform a measurement, but I might not know what physical system I'm preparing. So as a theorist, I'm imagining like these things are literally just boxes, and the quantum state is a label for this preparation box. So what is the information that I use to be able to predict the outcomes of experiments? So I need to know this row, this label on this preparation box, so that I can calculate the probabilities for the outcomes of experiments. So the forward process, if I know everything about it, that's deduction. That's kind of standard calculations that we can do. The reverse process is called induction. So in deduction, there's a unique answer. If I know the quantum state, if I know the channel that it's going to go through, And if I know the measurement, I can put all of these things into this trace rule and do the calculation. And if I'm using a computer, then it'll give me the same answer every time, and it will be unique. There's a correct answer. Now, the inverse process is much harder because there's no unique answer. So there's an example here. If I perform some measurements that's specified by some set that I've labeled EK, I might see outcome 1, then I might see outcome 3, then I might see outcome 1 again, and then I might see outcome 1 again. So I'll see this list of outcomes, and the task is to find out what that preparation box should be labeled. What is the quantum state I should associate to that preparation procedure? And there's no unique answer because quantum physics is a probabilistic theory, so there are many rows, quantum states, that could potentially give those outcomes. All that has to happen is that those outcomes are possible, right? So long as I assign a quantum state such that those outcomes are possible, then someone can't come along and say that that's invalid. So the only thing that's invalid is if I assign a quantum state where one of these outcomes that is actually observed is literally impossible, in the sense that if I calculated that probability, it would be 0. So long as I assign a state rho for which the probability that I would have calculated those outcomes for is not 0, then that's in some sense valid. But really, we want to find the best quantum state amongst all the possible allowed ones, or the most probable quantum state. So this problem of induction is an old problem. Of course, goes back to Laplace and probably before, and well, people still argue about it today. I'll just also point out that there's other options, right? So we might know what the state is, and we don't know what the measurement is. This is called measurement tomography or detector tomography. We might not know what the process is that happens in between the preparation and the measurement. This is called process tomography. And well, we could, be in the situation where we don't really know anything about anything going on. And there's ways that you might think that this is impossible, but of course this is what experimentalists do. I mean, there isn't something written in English on electrons that says what state one should assign to them. So when we enter the lab, of course, we don't know anything, and we have various heuristic procedures and expertise built up over the many years, 100 years of quantum physics on how to start to assign labels to these things. But there are now procedures that attempt to solve this problem in a more, let's say, I don't want to say rigorous, but in a more, a more sort of not requiring intuition of physics sort of fashion. One of them is called gate set tomography. Okay, so there's lots of themes in tomography, right? The task is to give labels to these boxes, which we color black because we don't know what we should ascribe to them. And one might ask, okay, well, what is the best figure of merit? How do I assign the goodness of an estimate? Given such a thing, what estimator should I use? There's lots of options. You may have heard of maximum likelihood tomography. You may have heard of compressed sensing. You may have heard of various machine learning type techniques, Bayesian tomography. Then another big area of research is, well, I can assign this box a label, but how confident am I? So that's a question about error bars. I should put error bars on my estimates. And then, of course, there's choices that one can make. I may not know what the state is, but I may have some control over how I can change the system, what process I can apply to it, what measurement I can perform. So there's lots of open questions there about what measurements should be performed. And as I mentioned, there are other areas of research where I can talk about smaller subclasses of states, and perhaps it's easier to estimate quantum states if they come from a smaller subclass. So this has a flavor of compressed sensing. And then, yeah, there's all sorts of new research on neural networks and quantum learning and things. So maybe I shouldn't have taken so long on this slide, because as you can see from the title, I'm not going to address any of this. So I'm going to do something completely different. And I'll just tell you the punchline right away, so you can go to a different tab in your browser, which I know you're doing right now, Mick. So the punchline is, we can perform a kind of adaptive measurement tomography without actually doing this state reconstruction. And that's important because this problem is extremely difficult. So the difficulty grows exponentially with the number of qubits. So, you know, it grows linearly with the dimension of the Hilbert space, but that's exponential in the number of qubits. So we're not going to envision doing tomography, at least completely reconstructing an unknown state beyond, say, in the 15 to 20 qubit range. We'll never do that. We certainly won't be doing tomography on quantum computers. So we can, what I'm going to show is maybe sort of a NISQI type tomography procedure, where you can have an estimate of the state without doing a typical reconstruction procedure, where you have a whole bunch of data and you're trying to analyze this data and solve this induction problem. The second punchline is that in doing so, we find a trade-off between what you might call measurement complexity and computational complexity. So I'll make this clear, but these are the two punchlines that you should have in mind. To put some numbers on it, if I think about standard tomography, so standard tomography just means pick a set of measurements which is sufficient to completely characterize the state. So this is termed an informationally complete measurement. Let me point out, if you're looking at this this graph, it's not written on the slide anywhere, but this is talking about pure state. This is the sub problem of if the quantum state is a pure state. So this isn't full density matrix tomography for this table. So if I'm doing pure state tomography, then I need 2D minus D, 2D minus 2 real numbers to specify a pure state, and I'll need on the order of D measurements, different measurements, POVMs or projection measurements, to completely specify all of those entries in the quantum state. When I perform these measurements, I have to store which measurements I'm doing to input into my reconstruction procedure. That's to store those measurement matrices, those POVMs will require D cubed in space complexity, and at some point I'm going to have to invert a D by D matrix. And well, you know, there's various ways to improve the multiplication and inversion, but let's just say, you know, and if you're going to use any built-in linear algebra solver, you're going to incur time complexity of D cubed as well. Now, to put some concrete, some quantitative numbers on this, what I mean by this trade-off, in self-guided tomography, you'll only need order D space complexity as the measurement algorithm progresses, and again time complexity order D. So you'll see where that comes about later on. But the penalty is that each time you acquire data, you have to change your measurements, and so you'll incur kind of measurement complexity cost of order n. Now, capital N here is the number of copies of the quantum system that you're going to use to characterize the state. So the number of times you press the button on the preparation box. And typically this is going to have to be much, much larger than D, because as you can see, the accuracy scales as D, order D, the dimension divided by the number of copies you use. So typically you're going to use a number of copies that's much, much larger than the dimension of the Hilbert space that you're trying to reconstruct. But you see that the accuracy in terms of the number of copies is the same. So that just comes from, you know, a statistical lower bound. I mean, you're not going to beat that with any procedure. So I'm not saying that either of these protocols could actually achieve this. It really depends on your implementation and, you know, yeah, how you implement the algorithms, but they have this sort of same asymptotic optimal accuracy. Self-guided tomography, you have this benefit of space and time complexity at the penalty of measurement complexity. Now, when I first started looking at this problem, I thought this ON was really bad, because when I would speak to people doing quantum optics, for example, to change the measurements, a graduate student actually had to go into the lab and manually put their hands on knobs of polarizers and beam splitters and change these. But you know, now we've progressed quite a bit in quantum technology to the point where these things can be automated. So perhaps this isn't actually a large penalty. Anyway, moving on, I will tell you exactly what this is. But first,
can you go back to the slides, the table that you?
Yeah.
So the measurement complexity of standard tomography is OD. Is it like you just measure a single copy because you have n copies, right? It should also depend on n if we consider the, like, I'm not sure.
No, I mean the number of different settings on my measurement device.
The outcomes of the measurement.
Yeah.
Okay.
Yeah. So I could, yeah, that's one. Yeah. For physicists, they probably imagine like measuring different observables. So I have a whole set of different observables. But yeah, in quantum information theory, you could just imagine, say, okay, let's put those all into one big POVM. How many POVM elements are in that POVM? And that's fixed. Like in standard tomography, that's just fixed. You just measure that same one for all copies. And then in adaptive tomography, you're changing it for every copy. Yeah. Okay, so here I have a picture of a clock. It's meant to represent a qubit. So think about it as just the XY plane, say, or let's say Z plane, because we're used to the picture of up being in the Z direction. So the ZX plane, and the black line, or the black arrow, is the true state. Okay, so we don't know what that is, but you know, let's imagine that, you know, we know we're doing a simulation or something, and we know that's the true state, and we start with some guess. So our guess is the green arrow. So how the intuition behind self-guided tomography is this. So when I perform a measurement, I'm actually going to perform two measurements, and they're going to be along, I don't actually have an arrow here in this program. Oh yeah, I do. Can everyone see that? My mouse?
It's tiny, but
yeah, okay. Yeah, well, when it moves, I'm sure it's easier for the eye to follow. Thanks, JP. So I'm going to perform a measurement along this axis. Okay, so a measurement for a qubit is just an axis in the block sphere. So I'm going to measure along this axis, this red axis, and this red axis. And because of the Born rule, it says that the number of outcomes you see in one direction versus the other is proportional to the cosine of the angle between the measurement axis and the true state. So that's just to say that you know, the arrow that's closer to the true state is going to see more outcomes than the arrow that's further away. So I'll see more up outcomes for this measurement than this lower measurement. And that suggests that, well, the true state is in this direction from my guess. So I should move my guess in that direction. Okay, so now I've moved my guess in the direction where I see more outcomes. And I do the same thing. I pick two measurements nearby my guess, and the one that sees a higher number of outcomes, I will take a step in that direction, and so on and so forth. Now, I think for for someone, especially if you're doing like optics, this seems very natural. It's almost like what you're trained to do without even being told, that when you're trying to align various things, you move it in one direction and you're watching a screen somewhere to look at, say, laser power. And if the laser power goes down, then you think, okay, well, that was the wrong direction, so I need to move in the other direction. So this kind of formalizes that in some sense. Now, of course, in this picture here, let's take a step back one step. So because, if I imagine that I'm doing these measurements very nearby to my guess, and I do, repeat it 10 times, say, then it's it could be the case that I see this measurement outcome more often than this one, right? Because quantum mechanics is a statistical theory. So of course, every time I perform this procedure, I'll get a different set of outcomes. And sometimes those outcomes are going to suggest that I step in the opposite direction. So I'm going to switch to a different picture altogether to illustrate that. So imagine that this doesn't have anything to do with quantum mechanics. It's just, imagine the simple problem where I have a function, f of sigma. Sigma is the horizontal axis. And I want to minimize this function. Okay, so clearly the minimum is down here at the bottom. And, I put a ball on this hill and it'll roll down, and, if it loses some energy, then eventually it'll just settle into the bottom. However, if I'm in a stochastic situation, and every time I ask, okay, well, what height am I at? I get a random answer. Then, of course, if I just say, instead of trying to minimize the function f, I try to minimize this red function, which is some sort of noise corrupted version of f. Now, don't worry about the writing. I'll say what that means in a minute. But now imagine that you're trying to minimize, the value on this red line. Then, a nice sort of smooth gradient approach isn't going to work. But you find yourself down here, and of course, that's not the actual minimum of f that you're interested in. Okay, so you can imagine, well, I'll just keep randomly sampling, and this minimum will bounce around, and on average it will be at the actual minimum, and that intuition is subsense correct. Now, to give you a sense of what the kind of noise that we're dealing with is, I want you to imagine that this green line that we're trying to minimize is a probability, okay? And the error just comes about from counting statistics. So this would be like shot noise in the case of optics, but it just comes about for the fact that when I perform a quantum measurement and I repeat it, that's just a Bernoulli trial. Each one is a Bernoulli trial, and if I repeat that k times, and I call my estimate of the probability, the very naive, the number of times I saw up over the total number of times I performed the measurement, then I'll see some sort of stochastic fluctuation around my true probability that I'm trying to estimate. So this is like for every point on the green line, I have a coin with a bias given by the value of that line, and I'm going to flip that coin many times and just do the naive thing and say the bias of the coin is the number of heads I see over the total number of coin flips that I did. And yeah, I mean, there's some finite statistics correction to this, but if k is large enough, then I'll just get some nice sort of Gaussian central limit theorem type error spread around the true value of that green line. Okay, so that's the first issue that you run into when naively trying to do this thing that I mentioned here, is that there's some stochasticity, and eventually I'll step in the wrong direction, and maybe when the green line is right nearby the black line, I'm just going to jump around that black line and I'll never actually converge. Now this is really simple in one dimension. So there's an added complication when we're talking about high dimensional estimation, as in quantum statistics. And so for that, I want to actually move to yet another picture. So now it's the same problem, but now we're just talking about like minimizing a function in 2 dimensions. So imagine this is a bowl, and these lines are lines of constant height in the bowl. So it's a bowl or a hill in 3-dimensional space. I can only represent it on the slides in 2 dimensions, and so each of these is a level plane. And if I start up here at the top, then where's my mouse? I start up here, and I want to end up down here at the minimum. And if I follow the gradient, of course, if I knew more than the first derivative, then I would take a straight shot down to the bottom. But if I followed the gradient, then I would take not the shortest path, but some other path down the hill, down to the bottom. And if every time I tried to evaluate the gradient and said, what is the height at this point and that point, then of course what would happen is I would just kind of, I would stay nearby-ish the green line, but I would jump around because I wouldn't be estimating the gradient exactly. And I would end up near the bottom, and if I wasn't clever enough, then I would just jump around at the bottom. Okay, so the protocol that I'm proposing, I will demonstrate how it works in this picture, and then we'll look at how it works for quantum states. So I start with a guess, okay, and what I'm going to do is I'm going to pick a completely random direction. So I'm not even going to attempt to find the actual true dimension of the gradient, and I'm going to pick a completely random direction in 2 dimensions. It's easy to show, but in higher dimensions it's the same. So in higher dimensional space, I just pick a completely random direction and I'm going to commit to stepping in that direction. So you can see already that we're avoiding the idea of trying to estimate a gradient in a high dimensional space, which require an exponential number of measurements, right? If I wanted to estimate the actual direction of the gradient, then I would have to do measurements in every possible orthogonal direction to get the sort of true place I should step in. So instead of doing that, what I'm going to do instead is just commit to stepping in a random direction. So I only need to do 2 measurements every time I estimate a gradient. Okay, so that direction I label delta K. And so I have these 2 new locations in my optimization space. And there's some step size, beta, and I'm going to step beta distance in that direction and beta distance in the opposite, so in backwards. So I've chosen a random direction. I step some small distance forward, some small distance back, and I perform my measurements at these 2 locations. The value of the function, which is just is stochastic, so it's a random variable, and I've kind of said the noise is different in each case since I'm doing independent measurements. So when I evaluate the objective function here, it gets corrupted by some noise. The plus just means the noise associated with stepping in the positive direction, and I'll get some noise associated with stepping in the reverse direction. Okay, and let's suppose that we're lucky and the value is lower for when I evaluate this function, and so then I'll step in that direction. and then we just repeat this process. I pick a random direction, step forward a little bit, step back a little bit, perform some measurements, and then whatever measurement was more favorable, I step in that direction. Okay, so let's get to quantum states. So here's a qubit, and I'm starting at the 0 state, so ket 0, so the z plus 1 z eigenstate, and let's suppose the true state is plus 1 x eigenstate. Okay, and each of the lines, the blue, purple, and cyan lines, is one run of the algorithm. Okay, so the algorithm will perform random measurement direction, choose random measurement directions, take steps in those directions, perform those measurements. On the left-hand side, each time I specify a measurement direction, I repeat that measurement 100 times. So if I see 90 up versus 10 down, then I'm going to say that the value of the function I'm trying to optimize is 9 over 10. Okay, so that gives me some precision, enhanced precision in performing these measurements. Okay, so you see that for the blue one, I've chosen the algorithm chose this random direction, and it took a big step in this direction. And then immediately right away, it chose another random direction, and it actually stepped, well, it's hard to say whether that was the wrong direction because it got unlucky and picked a direction almost orthogonal to the one it was supposed to step in. But you can see that, there's obviously some stochasticity to it, but eventually, and the key here is that the size of the step you take, and that includes where you do these two measurements, and the size of the step your estimate takes, both decrease as the algorithm progresses, and so you avoid this problem of bouncing around the optimal. Okay, so you take big steps at the beginning and small steps at the end, and these steps actually decrease as a power law. Okay, and then on the right-hand side, exact same thing, except each time I evaluate this function I'm trying to optimize, I'm performing more measurements. Okay, actually, sorry, this should probably be k here in the previous notation I used. So this is the number of repetitions per measurement direction that I'm using. And as you might expect, there's less variance when I use more measurements. So that's exactly what you would expect. But the algorithm converges no matter how many measurements that you use. You can go all the way down to 1 bit. If I do a single measurement, then of course the variance is going to be quite big. But now, so it's going to take more steps to get to the same level of accuracy, but I'm using less copies in that case. So it all kind of washes out in the end. But I think it's a good illustration and guides the intuition for how these algorithms work. Okay, so this works beyond just this simple example that I showed you. So it's going to work for a whole wide class of things that you can imagine doing, not just in quantum physics, but I guess in any sort of optimization procedure where you're including the ability to control things. Okay, so if I want to estimate a state, in this case a state or some other set of parameters, rho, the first thing I need is to be able to do an experiment where the controls of my experiment encode the thing I'm trying to estimate. So for pure states, it's simple in the sense that when I define a measurement direction, that's isomorphic to a state. So a measurement direction and the space of measurement directions and the space of states are the same thing. So by doing an optimization procedure over the set of measurement directions, I can also kind of hone in on the thing that I'm actually interested in, which is a state. So there's a duality there in the sense that the state is one of the measurement directions, and I have experimental controls which are labeled by the thing that I'm trying to estimate. Okay, so the second sort of, this is more of a desiderata. It's not completely necessary, but you must come up with some objective function that's easily deduced from experimental outcomes. So in the case of pure states, it's sort of direct access to this fidelity, this state overlap. If you want to do this for some other thing that you're interested in estimating, of course you could do full tomography and then evaluate this objective function, but that of course defeats the purpose. So the second, the first one is necessary. The second one is more of a desiderata, that you need to be able to easily deduce some objective function from experimental outcomes. And then the sort of obvious thing when you think about this for a little bit is that when I average over any sort of randomness in the experiment of evaluating that objective function, it must give me some sort of figure of merit that is optimized on the true state. So this D is some, say, generalized distance measure, which is optimized when my guess is equal to the true state. Okay, so I need to find an objective function that I can easily measure in an experiment, and if my guess is sitting at the true state, then on average that should optimize the function. That should optimize some function. So we need to find that as well. Okay, so those are the ingredients, and I'll show some examples of where these ingredients are satisfied. Okay, so the three that I'll talk about are pure states, mixed states, and estimating unitaries. Okay, so the ingredients for pure states is as was shown in the picture. So the experimental controls that I use are a measurement, and this measurement is just some projector. And in the lab, what I do is I measure that projector versus just everything in its orthogonal subspace. So it's sometimes this is called a test. So my measurement is it this state, or the opposite outcome is it's in the opposite, is in the orthogonal subspace. Okay. So for a single qubit, it's just a state and its antipodal state on the Bloch sphere. Now, the function that I'll try to optimize is just this naive estimate of the fidelity. And when rho is a pure state and sigma, as drawn here, is a pure state, then this random variable is, as I said, is just a coin toss with this probability given by the overlap of these two pure states. Okay, and I'll repeat that some number of times. K can be anything. So when I perform this measurement E, there'll be some randomness that's given by the probability of that, the overlap of that state and the true state, and whatever outcome that happens to be, I'll just say that the function I'm trying to optimize is that number of outcomes over the total number of measurements that I performed. And it should be it's quite an easy calculation, right? Because the expectation value of a Bernoulli random variable is just the probability, right? So it's just this parameter inside of the Bernoulli random variable. So the expectation value of this function is just the probability. Okay. Okay. So for pure states, this satisfies the requirements, and then the number 2, which is the desiderato, that this is extremely easy to do in the lab. Okay, so this is what I did in some simulations in this paper, self-guided quantum tomography. This picture is just the infidelity that you incur. So lower is better, and you see that you see this asymptotic behavior as promised. So this is the log plot. And the colors here are just increasing in Hilbert space dimension. So I don't remember if it's the number of qubits or the actual dimension of the Hilbert space, but in any case, purple is a qubit, and we increase in dimension as we go up. And you can see that as the algorithm progresses, the accuracy goes down, and then you eventually see some asymptotic behavior. So I think I've seen this thing so many times that it doesn't feel like it's counterintuitive to me. But I remember at the time, and every time I talk about this with people, it's always surprising that there isn't some noise floor, right? Given that, is there a question? I see something blinking. Oh, audio problems?
Yes, we couldn't hear
okay?
your last sentence.
Should I continue?
Yes.
Okay, so I'll repeat that. Yeah, what I was saying was, now that I've looked at these plots and done these simulations and worked with the experimentalists so many times, that it seems somewhat obvious to me anymore. There's no more confusion. Is that when people first see this, they expect to see some sort of noise floor beyond which you're not, because you have this stochastic optimization, and you expect to just jump around the minimum and never actually converge. But that you can show that, well, when you analyze the iterative steps of the algorithm, you can choose these step sizes that you take to guarantee convergence. So there's no noise floor. It'll just happily keep going down, getting arbitrarily close to the true state. And that's sort of the table that I'm repeating in the from the beginning. I can't believe with all this technology, there isn't a clock around me. Hold on. Let me just go from, okay, sorry. I just need to see the clock. Back to full screen. Okay. Right, so this algorithm is, remember, this is for pure states, and this was experimentally demonstrated with Rob Chapman, who I think is now in Vienna, and Alberto Peruzzo at RMIT, where they implemented this for one and 2 qubits in their quantum optics setup. So this is their picture of some iterations of the algorithm. You always, I mean, we're starting at the Z eigenstate plus 1 eigenstate of Z, and there's one true state over here, and the algorithm takes 10 steps and ends up nearby. And if the true state's over here, the algorithm takes 10 steps and ends up nearby, and so forth, right? For those 3 states, the fidelity is plotted as a function of the number of photons used for the self-guided tomography and for the standard tomography. And in this case, they found that that the self-guided tomography seemed to perform much better. And as an added feature that isn't really in this sort of complexity analysis, but is somewhat clear when you think about the fact that this algorithm is explicitly designed to be robust to noise, right? So we have I'm trying to optimize a stochastic function. And in doing so, I'm making it robust to noise. So now imagine that the noise doesn't only come from just the Born rule probability, the shot noise from the quantum measurement, but also some technical noise on how I define my measurement axis. Now, if I'm doing standard tomography and I make and I label my axis different from what the actual axis is, then you can see that I'm going to have some skewed picture of what my how I define my block sphere. So imagine I say I'm performing tomography measurements. I want to do tomography on a qubit, so I'm going to do poly measurements, and what I call X is what I call Z is up, and what I call X is nice orthogonal to up. But what I call Y happens to be some weird direction that's not orthogonal to the other two. Then, in fact, I'll never reach the true state no matter how many measurements that I do. But if this error is that I make when I perform these measurements, so when I go to set the measurement direction on my device, I make some random error, and that's off by some amount, then the self-guided algorithm actually doesn't care. It'll just keep happily going down and converging. And so the plot here on the far right is demonstrating that. So the dashed lines, or sorry, the dotted lines, the horizontal lines, are the fidelities. So what's happening in the lab is they're engineering noise on their measurements. So when the algorithm says perform a Z measurement, what actually happens in the lab is a Z measurement is set up to be performed, and then some intentionally induced error is put on that just to demonstrate the robustness to the error. So we see various different levels of error. So the fidelity of the projection that I'm meant to do versus the fidelity of the projection that actually happens. For the red line is 99.3%, 94.3% for the blue, and so on. Okay, and the dashed line also corresponds to the fidelity that's achieved, the maximum fidelity that you would achieve doing standard tomography, even if you use an infinite number of photons. And so you can see, after only a few iterations of the algorithm, you've already gone beyond what can be achieved with standard tomography. Okay, so that's pure states. It can also be done with mixed states. So if I'm trying to estimate a mixed state, then it's actually not much different. The measurement that I need to do is in the eigenbasis of my estimate. So I have some estimate sigma. I find out what the eigenbasis of that estimate is, and I perform a measurement in that eigenbasis. Okay. And when I perform that measurement, I'll get a random set of outcomes. One for each of the projectors in that measurement, and that's labeled zeta x sub k, and so I plug that in, and I multiply it by the log of the eigenvalue associated with that projector of my estimated state. Okay, so I've diagonalized the states. I know what the eigenvalues are. I know what the projectors are. I perform a measurement in that eigenbasis. I take the log of all of those eigenvalues, and I multiply it by the actual outcomes that I see when I perform the measurement. And you might recognize this as something that looks like an entropy term, okay, like a cross entropy type term. And of course, this is a random variable, and the random variable is now no longer a Bernoulli or binomial random variable. Now it's a multinomial random variable. And if my true state happened to be rho, then of course the probabilities for seeing one of the outcomes in this projective measurement is just the overlap, right? and I say I perform it, repeat that measurement k times. That k can be arbitrary. Okay. Now, another kind of straightforward calculation that you can do is that if I take the expectation value of this function over this multinomial random variable, I get this this term here, and you'll recognize that as the cross entropy term from the quantum relative entropy, or the quantum Kullback-Leibler divergence. Okay, and this thing obtains its optimal value when the estimate sigma is equal to rho. Okay, so that'll be very familiar for the quantum information theorists in the audience, but maybe not so for everyone else. But the point is that we're satisfying the desiderata and the requirements. So again, the thing I'm trying to estimate is the state, the kinds of measurements that I'm doing, encode descriptions of states. This is an easy thing to calculate from measurement outcomes, right? I'm just multiplying numbers together. And when I take the expectation value of that, I get some function which is optimized when sigma equals rho. Okay, so that experiment was actually performed as well for a qubit at Macquarie University by Sarah Kaiser, and I was working. We started this, I think, probably way back when I was a postdoc at the University of Sydney, where Chris Grenade was also postdoc. So he was discussing this project as well. But Sarah and Chris have now moved on outside of academia, and yeah, publishing papers on tomography is unfortunately not highest on their priority list. But Sarah, if you're watching, we got to finish that paper. Anyway, the data is all there. We just haven't written it up. But this is experimental data. The 100 here is the number of repetitions per measurement that I do. This is the number of iterations of the algorithm. And again, you see that it goes down, and here's a fit to the 1 over the total number of photons used. Okay, so that's mixed states. And then the last thing I want to talk about is unitaries. So to perform unitaries, it's a bit more subtle. So what we need is, holy, that's fun. I taped the green sheet to the back of the wall, so I had a nice green screen. Look at this. All right. So now you only get to see half of Seinfeld's apartment, for anyone that recognized that. So for the case of unitaries, I have some unknown unitary. I'm kind of mixing up notation here, so bear with me. So I have some unknown unitary u, okay? And the controls that I need, and the controls that I'm going to assume that I have, are the ability to perform a well-characterized unitary. Okay, so remember, if I'm going to do this self-guided technique, I need experimental controls that that are able to encode the thing that I'm trying to estimate. So so the experiment is I prepare a maximally entangled state, and I apply the unknown unitary, and then I apply some unitary that I know I can create on one half of the entangled pair, and on the other half I don't do anything. And then at the end I measure. I do the same as the original measurement that I talked about, this this test. So I'm going to test against this state here. Okay, and again, if you're kind of well versed in quantum information theory, you recognize this as something that looks like the Choi-Yamakowski isomorphism. So you'll already believe that everything's going to work out the same. But how that works, roughly speaking, is that in correspondence with the pure state case where I assign my estimate sigma, sigma is now like this V unitary in rho. The true state is now like the unitary that I'm trying to estimate. When I perform this, when I do this experiment, I'll get some set of outcomes, and each outcome is a Bernoulli random variable that's given by the overlap. Now I'm treating these things as super operators. So this is going to be the process fidelity between the two unitaries. That's the probability with which I see the outcome along this, the outcome that corresponds to this maximal maximally entangled state. And because it's Bernoulli, again, this expectation value is given by the overlap of these two unitaries in their sort of process matrix representation. Okay, and this is obviously optimized when V equals U. Okay, so we can do this. It's nice and clean when we try to generalize this to processes, so long as those processes are unitary. Okay, why did I think about going back to this problem? It actually started as a joke. This was I get 2 years ago when blockchain was in the news, and quantum machine learning was getting nice and hot. And so I thought about how would you combine all of these amazing, glorious technologies: quantum, machine learning, blockchain. And yeah, so it started as a joke, the self-learning protocol called Skynet. I don't even remember it was a good acronym. Let me just look it up. It was a good acronym. And so I did the simulations, and then there was a Twitter bot that sent out hashes called the Felix blockchain, and added to the data chain. And somebody said to me, well, that's actually, a non-trivial experiment to perform. Let's actually do it. And so we did it, and this was published. Sorry, I don't have the nice screenshot of like in the other ones. This was an experiment performed at the University of Science and Technology of China, where the results are because of this nice isomorphism between unitaries and pure states. I mean, much more difficult to perform the experiment because you needed to create this entangled pair and then do this kind of perfectly calibrated unitary that wherein you're attempting to invert the unknown unitary. But the results are the same in the sense that what you find is that in the self-guided algorithm, which is the green, 2 examples of different number of shots per measurement, 10 for the red, 100 for the green. So obviously, as a function of the number of iterations, you'll get lower by increasing the number of copies per iteration that you use. The green line is simulated. What would be simulated by doing full tomography? Now, interestingly, the reason that is simulated is because in the experiment it would have just taken too much time to get all of these data points, whereas the self-guided one, as I've been told from the experimentalists, it was very easy to implement. And again, over here we have what happens when in the unitary that I need to control, there's a random rotation error, right? So, and then again, the horizontal lines are simulated what would happen if you did standard process tomography, and you can, as you can imagine, you get worse fidelity as that amount of rotation error increases, and the self-guided algorithm will continue to converge. And again, after a small number of iterations, converges beyond what standard process what the lower bound on standard process tomography is. Okay, so so that's it. This is this is using an algorithm that comes from the classical optimization literature. It's a whole class of algorithms called stochastic, from a whole class called stochastic approximations, and you know, under a whole host of assumptions, you can prove convergence. But these assumptions are always the noise is Gaussian, or the noise satisfies some martingale property. It's never discussed in that literature, obviously, that you have the model of the statistical noise is coming from a quantum system. So that hasn't been discussed, and I haven't had the time to analyze it myself. So the first call to action is to actually come up with a formal convergence proof of this. You can't just apply the classical literature, although, you know, as you see in the experiment, it's a useful protocol, and all the simulations suggest that it's going to work. On that note, I've used one of, you know, a seemingly infinite number of possible stochastic approximation techniques. So perhaps another one works better in theory or in practice. So given that this, from what I've heard from the 3 experimental groups that have implemented this, it's remarkably easy to use, and takes far less time than standard tomography. So when, you know, if you consider using this, then and you have time to spare, or you have grad students to spare, then you could investigate some other algorithms, related algorithms, and not just maybe naively apply this algorithm. Okay, so remember the 3 requirements, 1 desiderata. The 3 examples that I gave you were pure states, mixed states, and unitaries. The question is, what else can you apply this to? Can you apply this to subclasses of states and get some sort of compressed sensing like benefit? Could you apply this to measurement, detector tomography? And then the one that I'm also interested in is to generalize this to full channels, not just unitaries. Okay, and then also when you're looking at this and trying to apply it to new areas, this function f is the thing that is the key. Can you come up with more efficient or more, in some sense, more feasible experiments? So the last one that we saw required, you know, an ancilla. Can we do this without an ancilla? That's another question that we're interested in answering. And so that's all estimation. These are all the ones I showed you, and what I'm suggesting here are all in this sort of tomography paradigm. So this algorithm I've also applied to quantum control, to actually control quantum systems in sort of a kind of automated feedback way, suggesting that these techniques can be used beyond just the tomography. So the question is, you know, what is the broadest class of optimization problems that we can exploit this technique to solve? And that's the end. Thank you for listening.
Thank you, Chris. And on behalf of everyone, I can play a clapping sound.
Thanks.
Yeah, okay.
Are we doing questions?
or everyone can unmute themselves and clap for myself.
Okay, thanks.
Question part. If you have questions, yeah, unmute yourself, please, and ask your question.
Chris?
Yeah.
Yeah, I want to ask a question. So I guess like in your algorithm, this some iteration procedure, you measure something with certain number of copies and get some idea of the system, and then you go into the loop and try again, right? But there's this like the cost is then first you need to do multiple number of measurements to get a good sense of which direction you should optimize with forward or backward. And I guess like there's freedom of choice. First, like there's a step beta. You didn't really go into detail how do you choose the beta, and then the other thing is I guess like how much measurement do you expend in estimating this?
Yeah.
In that particular step, and because like this in total the number would be the number of iterations and the number of costs in each iteration, right? So is it like only heuristic guesses that you use in experiments, or there's some general guideline you can follow?
Yeah, yeah, it's a good question. I think especially in the experiments that have been performed, they're all in optics. So you're doing something a little bit different in that, like, you're measuring the kind of photon flux. I mean, I'm pretty sure in all of the experiments, it's not just like strictly photon counting, right? Because you don't have perfect single photon detectors. So, but there you have the same problem, like, you know, what, yeah, per setting, how low should you go in photon flux? Like, what is the expected number of photons that you should see? So you're right that the total number of copies you use is 2 for each of the measurements that you do to estimate the gradient. At times the number of iterations of the algorithm times the number of repetitions that you're going to do these measurements for. Yeah, so that's the total number. When you look at the convergence proof in the classical literature of these similar algorithms, that choice isn't there, right? Because you just assume you have some noise model, right? The noise model doesn't come with its own parameter. But you know, if everything's sort of in the central limit theorem type argument, then you can kind of make the following argument that it doesn't actually matter how many repetitions you use per measurement, and I've observed this in simulations that when you saw some of the plots. So I'll show you one of the plots that is a function of the number of measurements. Yeah, okay, so the one on the left here. So obviously if I use 100 photons per measurement, I'm going to get lower infidelity than if I use 10 photons per measurement. But the point is, if I shifted the green line to the right, so that instead of iteration on the x-axis, I'm counting the total number of photons used, then the green and red line would lie right on top of each other, more or less. So that sort of raises the question: what is the optimal number? What is the optimal value of n? And my guess would be n equals 1, but you'd have to modify the algorithm in some sense, because you wouldn't want to take a step. You wouldn't want to increase the iteration number if I'm doing two measurements nearby and I see up here and up here, then the difference between those two is 0, right? So in reality, I don't take a step. But in practice, like in the algorithm iteration number increases. So you wouldn't want to do that. So my guess is the optimal thing to do would be to just measure here, and stop as soon as you see a difference. As soon as you see a difference, then you step in that direction. That would be my guess that in practice of the sort of optimal, like copy optimal protocol.
Okay, thank you.
Can I just follow up on that, Chris?
Mm-hmm.
But experimentally, it's easier to have higher n than more iterations, right?
Yeah, well, this was sort of my original, yeah, I kind of knew originally that this was going to be a difficult sell, like if you're trying to get people to implement your algorithm, because, yeah, at the moment, data is cheap and changing experiments is expensive. But that might not always be the case, right? Especially, so this would be useful in systems where the actual, once I've prepared a system, the gates that performing the gates and acquiring a single data point is quick, but re-preparing the system is expensive. In which case, like I can change my measurement settings easily in the time it takes to re-prepare the system. So that's sort of the one regime where I imagine this would be most useful, or any adaptive protocol will be useful, right? Where I guess there are systems that have this property that the preparation time is orders of magnitude higher than the actual gate times. So to acquire a data point might take a lot longer than to change the measurement settings.
Right. And then a different question is there? Do you know if there's any requirement on how close the initial state needs to be in order to get convergence?
No. So like most numerical algorithms, there's some like magic wizardry in setting the algorithmic parameters. That reminds me that I didn't answer Zhongfeng's second question, which was this beta and the step sizes. How do you choose those? So those, there's a range in which you can show, at least if you're using nice classical noise models, that guarantee convergence. But in practice, choosing the asymptotically optimal values for those algorithmic parameters doesn't often work in the kind of initial, the initial sort of iteration number. So yeah, like most numerical algorithms, just naively applying this protocol won't, you may converge, but you won't get the best results that can be obtained. So you have to actually tweak the algorithmic parameters. And the initial step, the very first step size depends, like the quality of the algorithm depends on how close you are to the initial state. But you can always sort of, the further you are from the true state, the bigger the first step should be. Of course, you don't know how far away you are. So I think this isn't something that I mentioned, but it is something that's been thought about, that you could come up with an adaptive, you can choose the parameters of the algorithm adaptively, as you go. So this is like all of what I've showed you now is an algorithm where all the algorithmic parameters are set and fixed throughout the protocol. But you can imagine changing these algorithmic parameters as you go. And that might get around this problem of, it's quite sensitive to the initial choices of the parameters. But yeah, I mean, another way to answer directly your question would be, it doesn't matter how far away you are, so long as you've somewhat optimized the parameters in the algorithm. And in all of the experiments that were performed, of course, we did lots of simulations before the experiment was run, so that we knew what to expect.
Right. But then if you're trying to find a state that you actually didn't know which is the true state, how would you optimize the parameters?
How would I do it in practice? So I would still run simulations, but I would run simulations like over a whole bunch of unknown states, and then just pick the set of parameters that work best, on average, and then recommend those. So there'll be like a generically good set of parameters I'm expecting.
Okay.
Yeah. So yeah. Do lots of simulations before doing the experiment. Measure twice, cut once.
Is there any other question? So if there's no other question, let's thank Chris again. And
Thank you.
thank you, everyone.